All right, we are going to finalize this course with a presentation on level set methods, which is a topic that is dear to me. I've done quite a bit of research to it about it, so we're going to have a hands-on exercise, and I'm going to try to show as many examples as I have, as I can within the time frame of this lecture. So let's get going. So first, to introduce in general level set methods and where they sit. In themselves, level set methods have nothing to do with porous media on their own. It's a general class of methods in applied mathematics. And above level set methods, there's general class of moving interface problems and how they're resolved. So you have many physical problems that can be described as some sort of moving interface. Of course, in porous media, we think of a moving interface as either a moving fluid-fluid interface, but there could be a fluid-solid interface, for instance, in case of precipitation on a solid, right? And there are a general class of numerical methods that are kind of tracking these interfaces of interest. So your the problem that you have to first agree on is, how do I represent interface, okay, before I can do something with it? So options are so-called explicit front tracking, where you discretize your interface, and at each time you have these points xi of t at that interface, and as time moves along, you have another set of points xi. And basically, you keep moving them basically according to Newton's law. What else? So but the acceleration at every point is some sort of forcing divided by mass at that point. There are problems with this, specifically splitting and merging. And as the interface kind of either expands or shrinks, your coverage of the interface or number of the points per interface changes. Right? And that if you don't have sufficient coverage, or you have too much of coverage around certain points, that's a problem. So basically you have, if you are moving, so if this is your initial interface and you have 5 points, okay, that you're representing it with, now let's say that you're expanding, and then your coverage is not as good, so your resolution is not going to be as good, and your interface will be choppy, and all kinds of physical problems will start from there because you don't have sufficient representation. Same way if you were going the other way, okay, suddenly you would have too many points and too much. So you kind of have to constantly reevaluate what these points are. And yes, there are actually there are methods that do that. They're called front tracking. It's funny, but I came from this department, Applied Math and Statistics at Stony Brook. Initially, I was in the group that did front tracking, and then I changed advisor. And this is the sort of the significant, it was a major group there at the time. And I switched the advisors, and then I never really had anything to do with front tracking afterwards. I did my porous media gig. And then I came here as a postdoc and started working with competing methods, which are level set methods. so every time somebody would ask me, "Oh, did you work with James Glim and front tracking in applied math over there?" I said no, and then I never actually went, or it just so happened that I never went back and gave a talk on level set methods in my home department. But I wonder if that had something to do with the fact that they're front tracking folk. Anyway. Another way we already mentioned in this course, it's level set methods. So you're basically embedding original interface into a higher dimensional function. Those are our images, right? And if you remember, we were then isosurfacing or finding surfaces where your image value is certain value. And that's precisely what the level set is, okay? So basically you have this implicit, this is your interface. You embed that interface in this entire domain as a function defined everywhere, and that function, for instance, is 0 on the interface and less than 0 inside, larger than 0 outside. And then basically you embed fed that in a plane here. And as you're shrinking and expanding, okay, basically your interface is moving on a higher dimensional surface once you add time to it. So this is now time, right? And basically you're then on a conical surface in time plus space. Now, if this surface was 3D to begin with, when we add time, that's 4D, that's impossible to visualize. But if I had 2D plus time, then I get 3 dimensions and I can visualize that. Right? So just think that, like, if I had the 3-dimensional surface that is evolving in time, I could still do this formally or mathematically, and it would be a surface in 4 dimensions, right? Except that here I can visualize 2D to 3D. I cannot visualize 3D to 4D, right? If you can, let me know. Okay. You can do only by doing a movie of it, right? And then you have time steps is different. So that's essentially you're adding a level of complexity to yours. So what was your, essentially this is a 1-dimensional object in 2-dimensional space. And you're using entire 2-dimensional domain to describe it, this function, right? So that cost is higher, but then your tracking, or what I call bookkeeping cost, is lower, right? Because then you actually operate with this function using a partial differential equation that you discretize everywhere, and you have good coverage in entire space, right? So you don't have these resolution issues. And especially this bookkeeping of this sort in porous media, forget it. I mean, it's not practical. And even for the regular problems, the problems that fall into this class of front tracking, it's standard sort of instabilities. Let's say that you have a heavy fluid on top of a light fluid. You're going to start having fingering into that. So these fingers and mushrooms, as they kind of evolve, they become almost like turbulent in their appearance. So tracking that interface is a nightmare. Right? And you need parallel codes for that, heavy parallel codes. And now if you would add a porous medium to it with its complicated surface, I mean, that's not going to happen, right? Not in this decade, maybe in next. Okay, so right now it's just too much. So in that sense, this absence of bookkeeping and just keeping the same grid all over the place, regardless of whether I have porous medium or not, is the benefit for level set methods. So often you will actually simply find that a lot of numerical methods out there are aided by the level set description of your interface, because that's a good way to represent an interface, whatever that interface might be. Okay? So a lot of methods will be sort of aided by this level set representation. In contrast, we have these Lattice-Boltzmann methods that we mentioned that are sort of particle methods. There's also smoothed particle hydrodynamics, which we don't have time for, but it also takes good old parallelization even for 2D problems. They move particles or some sort of assemblies of particles. Okay? And a lot of ideas kind of resemble kinetic theory an awful lot, okay? Where you have these particles that are moving and interacting in some way. So in those cases, we're not tracking the interface, okay? But we will just do sort of isosurface where some density is larger or bigger than a given value, okay? So density of those particles in Lattice-Boltzmann is where we were evaluating that interfaces between 2 phases, okay? So at the end, so you kind of recompute where interface is at the end of the simulation. Now I will show how level set method helped me actually do sort of quasi-static 2-phase displacement, even on a single processor without the requirement of parallelization, which Lattice-Boltzmann does require. Now, you have to give up viscosity for that. If your problem is capillarity dominated, then that can be okay. So there's always, with every method, there are benefits and then there are sacrifices. Now, level sets are essentially 3D versions of contours. If you went camping to Enchanted Rock, and if you live in Austin and you haven't made it to Enchanted Rock, that's a problem. Fix that problem before it's too hot, because as you can see, it's a big piece of granite, by some measures second largest in the world. First one is somewhere in Australia. But measure is a, do you measure by volume? Do you measure by height? Do you measure by areal? You can now argue who is first, who is second. But it's a large piece of granite, that much we know. And one of the largest. And now because it's granite, it's quite a hard rock. So all of the sandstone layers on top have been eroded in time. And even this granite, actually, you can see pieces of it kind of chipping off when you go there. But you go hiking up there. Here's people for scale. Okay. And you go hiking up here, and there are apparently some people on the top of this rock, barely visible. Okay. So basically, you go hiking up there. But now, if you come to the park and you get the hiking map, then you will see some contours. Okay? And you know very well, if you should know anything about level set contours, that is, avoid hiking in areas where those contours are really dense. Why? Because over short distance in X and Y, you're going to go change your height function really quickly. Okay? So each of these contours is a single height. Okay, so as I'm walking on a contour, and if you want an easy stroll, then pick a contour and just follow that contour. You will never change height. Okay? So where these things bunch up, you have a very steep gradient, and they're kind of rarefied. That's where you should go. So that's as much as you should know about hiking and contours. This is the same thing. So height is a function that is defined over this entire plane. Okay? And I can slice and dice that function at certain levels, and that gives me contours. If I had a 3D versions of this, so height would be height of x, y, z. It would be harder to visualize, of course, but I could find contours of iso levels of this height. If you're thinking in porous media or in general fluids, you would think of iso contours of pressure, right? Or iso levels of pressure in 3 dimensions. Those are often plotted in fluid mechanics, and so forth. All right, so this is something that is commonly out there. Now, what are level set methods about? They take this contour, okay, and they're defining this function as a function phi of position and time. Okay? And what you're evolving, there's an evolution partial differential equation, and you simply say, okay, time derivative of phi plus some forcing. And I'm gonna explain forcing in a moment. Gradient of phi, this is absolute value of the gradient, is equal to 0. Okay, this is something I can discretize. The whole trouble comes through f. Okay? And f is simply speed of this level set normal to itself. That means that this moving interface is moving at speed f times normal in normal direction. So either in direction if the f is positive, or opposite the normal if the f is negative. Okay, that's all. Now, if this works in any dimension, I just discretize the partial differential equation. There's an entire math course behind this, but but just discretize because, of course, depending on what f is, this could be a hyperbolic equation, parabolic, combination of both, and so forth. So we know in differential equations what class my function, my partial differential equation is, decides on the type of the method I'm going to use it. And that's basically a different course that you take for studying those. So it can be problematic, or rather you have to know what type of differential equation you have to discretize. But that said, it can be done. Now, we're not going to have any problem with things merging and splitting. Now let's get back to my front tracking. If I had 2 of these sections suddenly wanting, let's say they have 2 fluid blobs coming at each other, okay, and they're about to merge. So I tracked separately these 2, and now I have to identify they're about to merge, and then figure out, according to the forcing and whatever, what is my merged profile. Okay, I call that surgery. Okay, I gotta suddenly merge something, or I might have splitting. I mean, I can have drops of fluid falling from the faucet, right? So I'm going to constantly actually split off pieces of interface as we go. And so I have to figure out how to split and where's my resulting split. And that's, again, tedious bookkeeping. Now, in level set methods, you don't have to do that. So basically, you just cut at certain level. At different levels, you're going to have different topologies. So here I have 2 pieces of interface. Here I have 1. It doesn't matter. It just depends. Like your height function is there, and you just slice it. Same as at this contour. We can see that at certain heights, the highest values of the elevation, I really have only, I have this contour, I have this contour, and I have this contour, and I don't exist below that level as an interface, right? So it's just, but I have the height function, so I just slice it wherever I want. So I don't have to do any special treatment for evaluation of topological changes, which for porous media is the key. So just in terms of geometric quantities, if I have this level set function phi, then my normal is gradient, okay, divided by its value. So it's normalized gradient. Okay? Whenever I have a constant function, okay, this is the direction of the least change or no change. As I'm moving around this interface, I'm not changing the value of phi. Is that correct? Yes? Because it's an isocontour. Physically, gradient is always pointing in the direction of the largest change. So that's what physically gradient means. I'm not sure that that's the fact that most of us leave multivariate calculus with, but we should. Physically, gradient of a function points in the direction of the largest change of that function. Okay? So basically, where my function is not changing at all, which is tangential to this interface, is orthogonal to where the function is changing the most physically. Okay? So that even if you don't want to deal with calculus and how it looks like, that should be kind of intuitive to you. That the direction of the least change is orthogonal to the direction of the most change. Okay? All right. Thank you, calculus. Calculus actually means something. Okay? It does. We just don't get that after taking a course in it because it's too much torture to calculate these. So we forget the physical meaning. Okay? Now, curvature is divergence of this normal. And those of you who have taken transport with me, you know that I enjoy divergence, right? And divergence we get in every conservation law, because physically divergence collects everything that goes through an interface in and out. So if I was doing conserving mass inside of this, okay, divergence integrating around this would tell me how much actually went in or went out of this volume that is enclosed by phi. Okay? So physically, divergence collects that information. Now, mathematically, divergence is divergence of the normal, which is the gradient. So I can get this mean curvature as a whole bunch of first and second order derivatives. All I need to know that they're there, I can calculate them. Great. Moving on. So if I was actually implementing this equation with a function that is basically, so if I remember my Laplace equation, my pressure is equal to surface tension times curvature, correct? Well, this is my mathematical expression of the curvature of that interface. B0 will be my interfacial tension that I throw into the code. And A0 will act as my capillary pressure. And I'm looking for the equilibrium position where this is equal to 0. Okay? And then basically what that means is that this is going to be 0, so I'm looking for phi that is going to drive this to a steady state solution where this is 0 as well. Okay? 0 plus 0 is equal to 0. So I'm looking for non-trivial function phi that will balance out my capillary pressure forces and my surface tension times curvature forces. Essentially, I set these values and my geometry will respond with the curvature that balances them out. Now, if I was discretizing this, okay, I would have then this is my temporal partial differential equation. This is what I have as f gradient of phi. And f gradient of phi, and get this, this part is hyperbolic partial differential equation. This one is parabolic. If that flies over your head, just let it fly. But I need to have different types of different types of discretization. And this is, I'm going to take central differencing scheme for this, and I'm going to take essentially non-oscillating solutions for hyperbolic. What hyperbolic discretization means is that I'm going to take, everybody knows what forward and backward difference is. So essentially, if I'm moving, I'm going to go in your direction. If I'm moving, let's say that this is my coordinate system, and I'm moving in this direction, okay, at next time step. That means all these hyperbolic systems require is that if my wind is blowing in this direction, I'm going to take the derivative that is going backwards in the same direction. Okay? So if I'm taking information from the previous time step, the time step should be, in this case, this is a backward difference. Okay? But if I'm moving in this direction, okay, then I should take forward difference. And I'm going to switch backward to forward how I discretize my problem depending on how my wind blows. Otherwise, if my wind is in this direction and I'm taking history from that direction, I'm going to get solutions that are not physical. I can do it mathematically, right? But it's not going to converge properly, and it's not going to depend on my history properly. So that's really all this hyperbolic discretization means. You have to always evaluate where you're going and take your backward or forward central difference depending on that value. Okay? So you just have to be ready to switch. Okay? So that's hyperbolic discretization. Parabolic, you just take central difference all the time. Okay? No worries, you take some from back, some from forward, and you center it on the stencil. Okay? Now, if you've never done discretization of differential equations, just forget everything that I said. It's all right. So we need to do this, and there's certain details if you want to implement this. You have to always keep this normal close to 1, otherwise you're going to introduce a whole lot of round of errors. And so you always kind of tend to reinitialize your function or replace it with a function with a well-behaving gradient. End of story. All right. And there's this toolbox that you have just downloaded that can help you explore this in MATLAB if you wanted to. There's also a LevelSet method library that I've been involved with, which is C, C++, Fortran in a Unix-like environment. All right. So there's this sign distance function. This is just this requirement that your normal, the gradient would be close to 1. So you can sort of in place solve another partial differential equation that will ensure that it's happening. Otherwise, your solution is garbage. And once upon a time, without having taken a course in LevelSet methods, I was implemented this, and it took me 3 weeks to realize, oh, I have to reinitialize. So 3 weeks of looking at garbage until things cleaned up. All right. So, but you've all encountered in your research points like that. You're just banging your head against a wall, figuring out what's going on. All right. So this is reinitialization. So there are multiple methods for it. I'm not going to go into details here. So we've already mentioned some LevelSet methods for segmentation. It's a moving interface problem I could figure out. And the moving interface, if you remember, is going to slow down when my gradient is high. So I have gradient of the values here very high. So I'm going to slow down and kind of try to nuance around this boundary. Or I'm going to move rather quickly where I can. Okay. So basically, I'm going to speed through this part faster because my gradient is relatively constant. And you could include a curvature term or a little bit of surface tension behaving for smoother behaving interface that is literally going to behave like an elastic band. And there's a paper, Richard Tsai happens to be a professor in our math department, but he's from Stan Osher group. Stan Osher and James Sethian are original creators of the level set methods in 1988. So by now these are two mature methods. They kind of both specialize in different types of these methods, and there are books respectively by each of them on the topic. All right, now let's see examples of this method that I've figured out how to use level set method for. So I'm interested in capillarity dominated fluid displacement. My guiding physics is Young-Laplace equation. So my capillary pressure, which is difference between the two fluid pressures, is sigma, interfacial tension, plus kappa times kappa, where kappa is mean curvature. Now I'm going to remind you, we went over this at some point, but I'm going to repeat it. So basically when I have interface, I have in any two orthogonal directions, I can look at the radius of curvature. So in this particular case, this is a saddle interface. This is one curvature, okay, and one radius of curvature. The radius is here. And this is orthogonal to it. Okay, so you can see two planes orthogonal to it. And this one and that one, they obviously have opposite signs. Now I can figure out which one's positive, which one's negative. But if they're of equal radius, then I'm going to have here 1 over r minus 1 over r. And I'm going to get a 0. So this is technically a zero curvature interface, or at least at this point, which is not how you visualize to sell to yourself something that is not curved. Right? Zero curvature means not curved. And our plane is not curved. And it's flat everywhere, okay? And it has a zero curvature. So plane is only one possibility. I can get infinitely many possibilities here. Welcome to fluids in three-dimensional porous medium. So in 2 dimensions, I have only one solution to zero curvature. That's a straight line. Okay? In 3D, I have infinitely many. In 2 dimensions, I have only one solution to a surface that has a constant positive curvature, 3, okay? It's a radius of it's a circle of radius 1 over 3. Okay? In 3D, I have infinitely many possibilities to figure out 1 over, surfaces such that 1 over r1 plus 1 over r2, with allowing both of these to be either positive or negative, is equal to a constant value. So actually this surface, so you can see traces of a sphere. This is basically interface kind of pushing in between spheres. I removed the spheres, but I left them where they contact the fluid, they're gray. Okay? But you can see fluid around the sphere contact here, the fluid around the sphere here. So this interface here, okay, this interface has a constant mean curvature, but variation of the individual, this is principal curvature number 1 and principal curvature number 2 is shown from orange to, and I forgot to write down this, but this goes from -1 to 3 or so, and these are also positive and negative. Okay. They all average to a single constant mean curvature. So fluid figures out, and this is in sphere pack, so obviously this is what typical fluids figure out too if I have a constant mean curvature. Now again, physically, constant mean curvature surfaces as a geometrical point of where they meet is physically they minimize area. So if I had a given volume and I looked for something of a certain surface of certain area around it, okay, the constant curvature surface minimizes area for a given volume. So physically, that's what fluid is going to try to do. If I have 2 different fluids that are not mixing together, they're going to try to minimize energetically, they're going to try to minimize area in between. Okay? Because having an area is expensive, energetically expensive. Okay? So I'm going to tend to this constant mean curvatures. And if I don't have a volume constraint, then I'm tending to a 0 mean curvature. But if I have a volume constraint, then it's some constant value that is preventing things from shrinking completely. Okay? All right, so we know the terminology of wetting, non-wetting, drainage, and imbibition. That's everybody's familiar. All right, so this is our level set methods. Now let's go back to our digital rocks framework and see how this fits in. We know that our objective is in general to obtain properties such as capillary pressure saturation curves, permeability estimates, and so forth. And we also want to understand pore scale behavior. One thing that this method is very good for is trapping, and also connectivity and distribution of fluid phases. So our geometry, well, now you are experts of how to incorporate geometries, but it could come from some model porous medium, such as sphere pack, which is described analytically, or it could be from an imaged medium. So in such a medium, this is a very simple throat in between two disks in 2D. This is how I would initialize. I would initialize my interface as right here. And then I want to basically increase the capillary pressure and see where am I going to find the interface. Okay? And this first point here, I alternate red and green colors. Okay? So first red one is the solution to that. Then I increase the capillary pressure a little more, and I get the second one, which is the green one. And third one, fourth one, and so forth. Okay? And then I'm here. And this is my sort of critical point. This is where I'm kind of most constricted. I'm in a throat. And at this critical point, if I increase capillary pressure a little bit, I'm going to lose my footing if I'm the fluid going in. And basically, my next stage is right here. Now, this is this topological difference, right? I went from interface that was a single interface to interface that had two pieces. And I'm now aligned. This throat is drained. Okay? So this is my critical point, and this is what we typically look for to describe porous media. This is as I'm increasing the stages of mercury intrusion, right? This is how my interfaces are sitting in my critical throats, and then I increase, and then I go through. And I keep doing that. Now, the only thing, so basically at each point I'm just stepping through increased values of this capillary pressure. That's all nice and works nicely. The only point like that I had to like at the beginning here, unfortunately in that mathematically, no interface is a perfectly fine solution to that, to that equation. So my interface, if I don't have enough pressure right here, my interface will leave the domain. Okay. Well, granted, that's going to happen in the lab too. If you don't give it enough pressure, the interface won't go in, right? And in order to find that, what's called bubbling pressure often, like the entry pressure for my porous medium, I have to give it what I call an exponential push here. So this is just a mathematical way to kind of give it a larger push until I get certain volume, target volume is Vm of it inside. And it'll figure out the solution somewhere, and that's then my starting point. Okay. So it's not perfect entry pressure, it's not the smallest one, but it's something larger than the entry pressure, simply so that I can find my footing in the porous medium or else. Okay? So it's just a shortcut. Or otherwise, you keep trying until you get in. All right. And then final thing is, how do I resolve this Wall boundary condition? Okay. Wall boundary condition, I simply say I have a static function that is defining my porous medium, and I'm going to call it psi. And I'm going to, at every point, so my non-varying phase or my pore space is both are where phi or psi are negative. Okay? So if I take a maximum between the two functions, the moment my non-varying phase attempts to enter this medium, solid medium, this is where this psi is positive. If non-varying attempts to become negative here, this maximum will fix it. I'm going to be reset to the value of psi. Works like magic. And I effectively end up with two things that align. Therefore, I have a zero contact angle. Two things being two surfaces. Okay? And that's my claim to fame, folks, in 2006. All right. I'm older and wiser now, and this doesn't work in unconventional media because I don't have connected pore space. So in the meantime, I have expanded my range of methods I work with. This one was really cool while it worked. So here's a classical paper by Lenomar and Zarcon. It's the paper on simple pore network modeling. And basically, if I have this interface going into, this is a very simple pore network where I have a pore and throats attached to it, and everything is nice and straight like a micromodel. Okay? And then I could actually have different interfaces depending on where I'm coming from. If I'm coming from here and I go through this point, if this is a wider channel, okay, or if I'm coming from two cases. So let's look at the imbibition after this. Okay, so if I'm imbibing from this stage, okay, so I started drainage and I drained to here and I'm imbibing, this is the way I came in, I'm gonna go back the same way I came from. This portion is still reversible. Okay? Same thing as this, like I can see these stages of drainage. Now, however, if I actually push through one of these channels, then I'm gonna have an interface like this. Okay? And if I start imbibing from an endpoint like this blue one, then I'm gonna come back to this, and I won't be able to imbibe anymore at positive pressure. So there is sort of always going to be a residual fluid here in this very simplified form. Whereas if I actually started imbibing from this position where I had only two of these, okay, so this was much wider than here, so I actually I would also go back and I would be never able to imbibe beyond this point, so there would be some residual. So this is in 2D. Now, if you do in 3D, just to say, okay, I'm gonna push through. So now let's put this in. Essentially, what I'm pointing out here is depending on the curvature you start your imbibition from, okay, you might have different outcomes at the end of imbibition. And we know that very well from our mercury intrusion and our capillary pressure scanning curves. And basically, the moment you actually split the interface in two, you made an irreversible change thermodynamically. Okay? You can't get that back. You can't get that back in the same form. Now, let's look at a succession of multiple pores. This is a simple two-dimensional fracture. And I have my stages are in green and red. There are so many of them that they're all kind of pile up here, but this is my interface. So this is my first throat, and it takes me a moment to go through. And then once I push through here, this is called Haynes' jump in porous media. Haynes studied this first in 1930. And these things, you can actually literally hear them if you're doing an experiment in the lab. Like there's a whoosh sound as this interface is pushing through, because there's an instability here, okay? I'm unstable, I kind of push through really quickly, okay? If this is a really, really tight throat, okay, this is where I might have interface closed behind me, okay, depending on what kind of gradient I create. And basically you could actually have a bubble happen here. That's so-called the Roof's criterion, and that's how we get foams, right? We push them through tight constrictions, and you're gonna actually get things foam up. So, but here it didn't foam, it just went through if things were sufficiently slow. And then this is my next tight constriction. I keep going, next one, next one. Let's put this together in a movie. In a movie, you will see non-wetting phase as red. And hopefully it will play. Oh, now it plays. For 2 years or so, this just wouldn't play over a projector. Things are changing. Whoosh, whoosh. Yeah, we can have sound effects to this movie. All right. Now let's go back. It's a converted. Sure. I'm going to place this on my desktop and see whether that behaves better later. So it was kind enough to convert it for me. Look at that. Technology is improving. Now let's do imbibition. Ah, there's my mouse. I converted the movie and lost my mouse. Oh, come on.
How much time do you take to solve these two systems?
Oh, this small stuff is possible in MATLAB, not a problem. I'm gonna have to go to my video because for some reason I can't get mouse to. So this is my imbibition. Okay. So I'm gonna now start from the drainage endpoint, and it's gonna take much longer. Okay. And what's interesting is that it's gonna happen at different. Sure. It's gonna happen at different curvatures. Okay. So I can see. Oh, MATLAB. And now I can see here that basically my drainage was controlled by throats, okay, and the curvatures corresponding to these throats. Imbibition, however, it's going to take a long time to reduce curvature here enough so that actually this interface and this interface slide together down this grain. And when they touch, that's when instability happens. And basically, I jump to the next position that, in this case, happens to be supported by these two grains only. Okay, and then a couple of others. And here, when this interface merges with this one, and this with this one at these 2 points, I'm going to lose my footing and imbibe an entire pore. Okay, so this is imbibition of a pore. So imbibition in a pore is basically guided or dominated or directed by the radius of that pore or size of that pore and geometry of that pore. So yes, so where the surfaces are, and do I have enough footing to actually support the next curvature that I'm looking to support? And if not, I go down to this next throat and figure out where my next stable position is. Okay? So these imbibition events in pores are also unstable and also irreversible. Okay? So drainage is dominated by throats, imbibition by pores. That's something that we know, but this is basically confirmed. All right, well, I guess we're going to try that